Here you can see liquid oxygen being attracted into a magnetic field. Why does oxygen show such a behavior? Is it paramagnetic? Well, oxygen is paramagnetic. It is due to the presence of unpaired electrons in oxygen molecules that it gets attracted to the magnetic field. How will you explain the presence of unpaired electrons in a molecule? In this video, we will learn about writing the molecular electronic configuration based on the molecular orbital theory and predicting the magnetic properties of a molecule. First of all, we will look into the energy level diagram based on molecular orbital theory. The 1s orbitals on two atoms combine to form the sigma 1s bonding orbital and sigma star 1s anti-bonding orbital, as you can see here. This is a sigma 1s orbital which is situated down here, and this is a sigma star 1s orbital which is situated here. Similarly, 2s atomic orbitals on two atoms combine to form sigma 2s and sigma star 2s molecular orbitals. Due to the head-on overlap between 2pz orbitals, their interaction is stronger than that between 2py and 2pz. So, sigma 2pz lie below pi 2px and pi 2py. As you can see here, sigma 2pz is below pi 2px and pi 2py. And sigma star lies above pi star 2px and pi star 2py. Note that this arrangement is true for molecules with 15 or more than 15 electrons. However, for molecules up to 14 electrons, say for example diatomic molecules like boron, carbon, nitrogen, etc., the increasing order of energies of various molecular orbitals is as shown here. You can see the pi 2px and pi 2py have lower energy than sigma 2pz. Remember, while writing the molecular electronic configuration, electrons are filled in the order of increasing energy of orbitals. Hence, only after placing electrons in pi 2px and pi 2py, sigma 2pz will be filled. In fact, the stability of the molecule also can be predicted from the molecular electronic configuration. The molecule is said to be stable if the electrons present in the bonding molecular orbitals are higher than that in the anti-bonding molecular orbital. Next, we will learn a new term which is called bond order. Bond order is 1/2 the difference between number of electrons present in the bonding and the anti-bonding orbitals. The value of bond order can also predict the stability of molecule. A positive bond order means the molecule is stable, while a negative bond order corresponds to an unstable molecule. Basically, bond order gives the nature of the bond. The bond order 1, 2 and 3 corresponds to single, double and triple bond respectively. Obviously, bond order gives the strength of a bond. That is, as bond order increases, bond strength increases. Subsequently, bond length decreases. Finally, we will learn how molecular electronic configuration can predict the magnetic nature of molecules. The presence of unpaired electrons in a molecular orbital makes the molecule paramagnetic, while absence of any unpaired electron makes the molecule diamagnetic. We will learn this with an example. Consider oxygen atom. The atomic number of oxygen is 8. So, the electronic configuration is 1s2, 2s2, 2p4. Then, the number of electrons in oxygen molecules will be 16. Now, you can write the molecular electronic configuration of oxygen molecules as follows. Based on this electronic configuration, the bond order of oxygen may be calculated as half into number of electrons in bonding molecular orbitals minus number of electrons in anti-bonding molecular orbitals. There are 10 electrons in the bonding molecular orbitals and 6 electrons in anti-bonding molecular orbitals. So, the bond order is 2. This shows in oxygen molecules, the atoms are held by a double bond. The bond order being positive, the molecule is said to be stable. Then, how will you predict the magnetic behavior of oxygen molecules? You have to draw the molecular orbital diagram based on the electronic configuration of oxygen molecules. As you can see, there are unpaired electrons present in the pi star 2px and pi star 2py orbitals, as you can see here. Two unpaired electrons are there. This clearly indicates the paramagnetic nature of oxygen molecules. Obviously, oxygen will be attracted by the magnetic field. Now, can you write the molecular electronic configuration and compare the stability of the following species?
Manorama Horizon. Learning made simple.